metric spaces. Yeah, so you have a distance function that that detects if points are the same or different. The distance is symmetric, and we have the all-important triangle inequality. And given x, d from oops.
Sir, you have not started the recording.
Right. Thank you for reminding me. I will just do that. Let's first put this over here. Okay, so let's begin.
Recording in progress.
All right, so we've defined several terms. Open ball Brx of radius, a positive radius centered at x and x. And what are the closed sets? What is a closed set?
X minus an open set.
Right, so just complements of open sets. So this collection defines a topology on X. Gives a topology. Maybe we'll just write it down here. These two are really equivalent pieces of data, right? Gives a topology X. And what was the topological space? Collection of I'll put it in quotation marks, collection of open sets, that is closed under unions and finite intersections. Okay, very good. All right. So I gave you several exercises last time, and I hope you did do those exercises. Some of these exercises will be in the homework. They may come in quizzes. By the way, maybe I should say that perhaps we should start doing surprise quizzes in class. Okay, so I'll take a call on that. For small weightage, but I think it will be a good idea if maybe from time to time I do a surprise quiz. Anyway, so what were the properties of closed sets? Let's just sort of go through it in lightning fashion. Because arbitrary union of open sets is open, that immediately means that by taking complements, that means that arbitrary intersection of closed sets is closed. And similarly, because intersection of two open sets is open, that means that union of two closed sets is closed. We also defined subspace of a topological space. So this was yet another exercise that I asked you to do. So subspace of a topological space X is S with collection of what open sets given by
The open sets of X intersected with S.
so U intersections S such that U is open in X. And I asked you to verify that this actually gives a topology. And then finally, there was this exercise that open in open is open, and likewise for closed, right? Let me not write it precisely, but we did write it down precisely last time, which is to say that if S is open in X, then a subset of S is open in S precisely if it is open in X. And the entire statement stays true if we replace all occurrences of open by the word closed. Okay. All right. So here is the exercise for you in class to keep you busy. So given a topological space X and S in X, define S bar is equal to the closure of S, the closure of S to be S bar equal to the smallest containing S. All right. So first part of the exercise is so let me follow my notes, making things up as I go along. So A for a metric space X so while I'm writing the exercises, I will not make any commentary on that. So you can try to. And B for function
we can also define limit in topological spaces as well, right?
I would rather not do that. So for
Instead
a function
of taking balls, we can just take the open sets.
Remember, in our definition of limit, we have the notion of a size. We want something.
Yes.
So it's possible, but let's not do that. So for a function between,
we have a concept of limit point sets. Limits point can directly come from.
That's what we are coming to. Okay, so let me just set up the exercise and then we will begin with our class development. So show the equivalence of following conditions. So we have defined for a function to be continuous, right, between metric spaces or between. So what is the definition of continuity at a point? We did write this down, didn't we? For metric spaces, yes. Okay, all right. So let me not repeat that because we are coming to it anyway. We will do this in class. I'm just sort of laying it out. F is continuous. That means it is at continuous at all points. F inverse of open set is open. F inverse of closed, and F of S bar is equal to F of S bar. And this is interesting because there is a mistake in some of these somewhere in here. All right. So I have introduced a mistake in here. So if you're doing this exercise, your job is also to find out this mistake. Something is not quite right. Okay.
If inverse of closed is closed, but open is open, is it?
Sorry, say that again, please.
If inverse of closed is probably closed, but also if inverse of open is also open.
Right, that's what I'm claiming at least. So
I think one of them is forward.
So I'm going to say check. All right. Anyway, so let's begin with our class. So this is just an exercise if you want to keep busy and not pay attention to the class. But this is where we are headed. All right. So one of the things. So where are we headed? So far, the notion of continuity that we have is really expressed in terms of epsilons and deltas. And then in one of the after class discussions, we did talk about how to express this in terms of balls. Okay. But there was yet another way in which you characterize continuity last semester. Do you remember in terms of sequences?
Yes, sir. We needed that a convergence sequence. Like if we take, so if it's from X to Y and we have a convergence sequence in X and its
Right.
limit is, let's say, small x, then f of f of xn tends to f of x also.
Okay, so might as well, yeah. So put these 5 conditions. All right. So this is where we are headed. We want to define continuity in terms of topology, and we'll see that there is a very nice description of this. So you see the 5 bullet points that I have given over here. Out of these, the middle 3 bullet points are really in terms of the topology, purely in terms of the topology. Okay. So this is where we want to get today. And then even beyond if we can. So let's get started. The very first thing is to define closures. Okay. So, and for that, let's define the notion of a limit point. So definition. X is a metric space. And S is a subset.
So what is the TFA in the SSS part B? Acha, the following equivalent.
Right. So TFA just means the following are equivalent. Right? And again, remember this exercise, we are going to get to all of this in class. Okay, so given a subset of a metric space, what does it mean to be a limit point of that? And it means the following. If X is a limit of a sequence of points in S, that's the idea. But I want to make a small change over here. if there exists a sequence Sn with all, sorry, I keep making a mistake here. Such that the limit of this sequence is X. And this is morally correct, but it's not quite. So I want all of these points not to be X. So each Sn is different from X. All right, so just take a moment to read the definition. So what is the picture? The picture is that here is X something, here is S, and here are points, and here is this point X. And the idea is that there are these points S1, S2, S3 that tend to X. So the way I have drawn this, X, it's sort of deliberately left unclear. This point X, so just comment, X may or may not be in S. For example, if you take the open interval 0, 1, then 0 is a limit point of that. As is 1, correct? Because you can just take, for example, if you take 0, you can just take the sequence 1 by n. And the limit of that sequence is 0. Notice none of those points is 0. The limit of that sequence is 0. 1 is a limit of 1 minus 1 over n, that sequence. How about the point half? For the open interval 0, 1, is the point half a limit point?
Yes.
Yeah. So notice that I'm not saying anything about, so this point may or may not be in the interval. I just do not want the points, the elements of the sequence themselves, I do not want them to be the point that I'm considering. I mean, the reason for this is that I don't want to, for the sake of this limit point, I do not want to consider the stupids. If the point S happens to be in the set, then in order to see whether this is a limit point or not, I don't want to take the stupid sequence, which will immediately become a candidate if I do not put that condition. Notice that if the point X happens to be in the set S itself, and if I do not take this condition, if I allow this, the elements Sn to come from arbitrary points in S, then I can always take the stupid sequence that converges to X, namely every Sn is X itself, right? So I do not want to allow this possibility in the definition, right? So I hope the definition is clear. Okay, all right. So this is a definition in terms of sequences. And the very first thing that
Hello, sir.
Yeah, go ahead.
Sir, then why don't we define it in this way that all the Sns are not X?
Yeah,
I mean,
but
if we want to rule out that.
But it's exactly the same thing. What I have done is the same, no? So this condition over here, that's what it is saying. Every Sn is in the set S, and I have removed. So I hope everybody understands the definition. The definition of this, what this notation is. Set difference notation. Okay, so shall I just write this down? So I'll just say notation. Okay. Notice that for this notation, the set B does not have to be contained in the set A. You're just taking the part of A that is not in B. Okay. So,
Yes, sir. I get it.
all right. So, let's start proving things now. So, claim. X is a limit point of S every neighborhood of X in X all right. So is the claim clear? The definition of limit point is made in terms of sequences, but now I'm trying to cast it in terms of topology. So I'm simply saying that every neighborhood of X in capital X, all right, so contains a point of S other than X. A couple of very simple remarks. Instead of the word neighborhood, I could use the word open set, because neighborhood is a set containing an open set. But an open set also is a valid neighborhood. So if every neighborhood contains a point of S other than X, then every open set does too, because an open set is a particular kind of neighborhood. And if every open set contains such a point, then so does every neighborhood. Namely, take an open set contained in that neighborhood. Such a point will contain whatever is desired, and so therefore so will the neighborhood. Like small set theoretic things. Okay. All right. So how do we prove such a thing? Just the shape. Okay. And what I'm trying to tell you here is that even before we come to grips with the statement at hand, just the shape of what is given allows me to start writing down some sentences. So it's an if and only if statement. That means I have to prove two separate things. First I get to assume what is written on the left hand side, and then I prove what is on the right hand side. And then I also have to do the opposite way. Both are required. So let's just do systematically. So let us say the proof of the forward condition. Right? What does this mean? This means that X is a limit point. So let X be S. And I have to prove whatever is given on the right hand side. Okay, so let's just set up the language. Because X is a limit point of S, therefore take a sequence Sn I'm just given that, right? There is such a sequence. The virtue of writing down such a thing is that I get to set up terminology. And what do I need to do? I need to show that every neighborhood of X contains a point of S other than X. So take such a neighborhood, right? Now, a neighborhood is something that contains an open set containing X. But I know that so what do I know about open sets containing X? Should I give a name to this open set? And I claim that I don't really need to. What do I know about open sets containing X?
They will contain a ball around X.
It will contain a ball around X, right? So, okay. So, to prove what we want, it is enough to show that any BRX intersection S contains a point other than X. So the reason why I'm writing all of this is to show you that many times for basic statements, if you just start writing things down and setting up the notation, it will lead you to the proof. Okay, so we are almost done. Where do I get this point of intersection?
By the definition of limit, there's a point which is less than radius. There are all eventual points are less than distance r.
Correct. Okay. So in fact, what he just said shows me that not only is there one point, there are infinitely many points. But let's write this down. So as X, oops, I keep making this mistake. As Sn goes to X, there exists N such that for all N greater than N, what is the key thing to write over here? Come on, this is where the proof is happening. So what do I need to write? At some point, so in words, what is going on? Beyond a certain point in the sequence, all points Sn are closer than R to the limit point X. So what do I write down?
Sn belongs to Br of X.
Correct. So let's just write down this in terms of the distance, right? So D X Sn is less than R. i.e. Sn belongs to Brx. So any such point will work. Maybe I can even take less greater than or equal to. In particular, S capital N is in intersection S minus X. So why do I get that this point is other than X?
By how you defined Sn.
Right, because you see, by definition of limit point, all of those Sns were different from X. Right? So this is the thing. All right, so proof is not particularly exciting, but we still wrote it down in complete detail. How about backwards? So what we know is that every neighborhood of X contains a point of S other than X. So maybe we can go a bit faster over here. So in particular, which neighborhoods am I going to take?
Open balls of radius 1 by n.
Right. So open balls of radii that shrink to 0, that will do the job. But what is the job that is required to be done? Let us see. I have to show that X is a limit point. What does it mean to show that X is a limit point? So let's write this down. We need to produce. So look at the definition. What is the definition of a limit point? I need to produce a sequence of points, all of them in capital S, but none of them equal to small x, such that the limit of those points is X. Okay. So we need to produce a sequence Sn in Okay, so this is a bad notation. Why is this a bad notation? Even subset is not good because you see a sequence is not a set. Why is a sequence not a set? For two reasons. One is that there is order, but the second thing is not all elements of a sequence need to be distinct, right? So a sequence in S minus X with limit of Sn equal to X. So just one phrase will do it. Take Sn to be in what? Yeah, so how do we finish off the proof? Okay, I'll just write it down because somebody said this. How do I know that such a, how do I know that such a, how do I know that such an Sn exists, such a point exists? Well, just by the hypothesis, no? Because every neighborhood is supposed to contain a point of, Sn in, sorry, so this is wrong. Not just in that, but where should I write it? In such a ball, but also in S and not equal to X. The hypothesis guarantees that such a thing exists because what I have, this ball is a neighborhood and it contains a point of S other than X. So this intersection is non-empty. Just pick any point in that. Now, I'm just going to say, see that limit of Sn is equal to X. Why is that?
Sir, can I say something? So when the n increases, we also have to ensure that the points that are previously chosen are not chosen again, right?
Okay. So does everybody understand the question? As n increases, we have to check that the points that are chosen previously are not chosen again. Is that essential?
I
Oh,
don't
no,
think
no.
it is, right?
Okay,
Because
sir, yeah.
n keeps
Right.
increasing.
Okay. So let us suppose that when n is 10, that means I want a point that is within distance 1/10, correct, from X.
We will eventually reach that end. Okay. Yeah.
So the point is though, suppose I choose something, let us say that is at distance 1/11 or 1/10.5. Okay. Then when n goes to 11, this point will anyway be not eligible. Correct. However, if at the 1/10 stage, that is, or the 10th stage, if I choose a point that is very, very close, let's say 1/1,000,000, then up until n reaches 1,000,000, I can keep choosing the same point again and again. There is no problem because it meets the condition. However, and as you observed, the moment I breach whatever distance I have chosen that point at, I will still be able to get some point, right? So eventually, whatever specific point I have chosen, I will have to leave that. The point is that 1/n goes to 0. That is what is going to drive the proof. Okay. All right. So are we okay with this? I would rather not write down this proof, because really you should be able to do this using epsilons and deltas. This is something that you practiced an entire semester. So if there are any questions, the time to stop me is now. Otherwise, I'd like to move. Okay, perhaps I can say this essentially because 1/n is decreasing, or maybe even the decreasing part is not really essential. That's the point. Okay, so let's continue with the claim. So the claim now, claim S bar, which I have defined to be the smallest set of X containing S, is equal to a bunch of things. So let's write this down. Okay, so all right, I'm just going to write it in some order. S union with limit points of S, which is the same thing as
So one question: how did we get that this B1 by n x intersection S minus x is non-empty?
okay. So let me just write this down, but I will scroll up to see for you to see the hypothesis. So notice what we are proving. We are proving the backward direction. That means what is written on the right hand side in the claim is given to me. See what it says? It says that every neighborhood of X, in particular, this
Okay,
ball
sir.
is a neighborhood, right?
Okay, sir. Okay.
Yeah. So, all right. And okay. So just take a moment to see this and let's prove.
Hello, sir.
Yes,
Sir, we need to prove these equalities are the same, right? I mean, they do not directly follow from the definitions.
exactly. So that's why it is a claim. So see the first equality here. The first thing here is the definition,
Yes, sir.
right? And but this claim, what the claim is saying is that I can really take any one of these as definitions,
Okay, sir.
right? So if you want, sometimes people write this as definition / proposition. So, okay. So what are the things to understand here? The first one is defined purely in terms of topology, right? Okay. As is the last one. Notice that the last one is also defined purely in terms of the topology. And the middle two things have something to do with the limit points. But so look at the second, look at the third and the fourth condition. This seems almost the same as definition of limit point, right? So what is different?
The SN may be X, like.
Right. So you see, the point is that this other than X business, which was there in both parts of the claim over here. Because you see, in order to be a limit point, I needed to have a sequence and no element in the sequence could be X itself. That was a part of the definition. And similarly, on the right-hand side of the claim, every neighborhood had to contain a point other than X. So you see, limit points are, so for limit points, this possibility that the point of interest could be X itself, that was excluded. Whereas here I'm not doing this. Okay, so how shall we prove this? Ideally, I would like to leave this as an exercise, but maybe we should do at least some of this in class. Okay, so I have read all the comments that are here on the side. We will come to everything. So any ideas how we can go about proving this? You see, we are saying that 4 sets are equal to each other. If you want to do this in sort of the dumbest possible way, just without even looking at what the 4 sets are, we can show that each one of the sets is a subset of each one of the other sets, right? But do we really need to do that? No. So let's call these sets something. I don't know.
Sir, what is smallest in the first sentence?
Sorry. So what is the what?
Smallest, the word smallest.
Okay. What is the correct? That's a very good point. So smallest closed set of X containing S. So it's a very good thing. So I can say that, I want an animal that is, that has certain properties. It has wings as well as 100 legs. Just because I say that I define such an animal, or I can define a unicorn, does not mean that it exists, right? So his point is that what does it mean smallest? So can somebody answer this?
So the intersection of all the closed sets which contain S.
Okay. So you see, there is actually an observation over there. So notice. Intersection of all closed sets containing S is automatically. So why is it closed? Why is this set closed?
We proved it, sir.
Or rather, right? We showed that it was that in arbitrary intersection of any bunch of closed sets is closed. So this is automatically closed. And it is automatically the smallest closed set containing S.
So does this mean any subset of S bar has to be open?
No, I'm not sure I understand the question. So just think it through and can you explain where it is coming from? Let me write the sentence in the meanwhile. Notice that is automatically closed and hence the smallest So this is just set theory. You see, because if I call this intersection, let us say T, then T is an intersection of all closed sets containing S. But T is also one such set, you see. Because intersection of all closed sets containing S will still contain S. And it is closed. So therefore, it is also a closed set containing S. So the intersection of all of these sets is also a member of that intersection. Right? So it is the smallest closed set containing closed set containing the set S. Sorry. Okay. Okay, so I hope I have answered this question. What does it mean? So I should really put that in quotation marks. Smallest closed set, right? And this is the answer. So I put a star over here. That is the answer. Okay, any other question? So how shall we go about proving this? Let's give names to these things, okay? So let's call these conditions whatever.
So we just need to prove that each of those three sets is closed and is a subset of the smallest closed set of X containing S, right? Like
Okay,
if we
so
had
right. So one proof strategy that he's suggesting is that show that each one of these sets is closed. And will that do the job?
and we have to show that they're like, let's say, subsets of the smallest closed set of X containing S. So maybe if we were to show that for one of them, then we could show that the other two are subsets of that set. Because I mean, yeah, that should do the trick, right? Like showing that one of the sets is in fact the smallest closed set and then showing that the rest are subsets of it.
Okay. Not completely sure what your strategy is. So what shall we, so which one shall we start with?
I think proving that like the closure of S is in fact the smallest closest set of X containing S is like that one. I think we just have to prove it a little more, let's say, from more fundamental ideas. I don't know, but the other two, if we prove that those are subsets of, let's say, the closure of S, then
so I'm just going to give some, I'm just going to give some names to these sets, just ad hoc here. A, B, C, and D. So we can start talking about these. So what do you want to show now?
Okay, so what I want to show is that first of all, B is A, in fact, right? That B and A are the same, and then show that C is a subset of B and D is a subset of B, or
yeah, but why will that show that they're equal? Maybe they're proper subsets.
But if they're subsets of the smallest closed set of X containing X, then they are in fact, and they are closed. The fact that each of them is closed and they're subsets of the smallest closed set means that they are in fact the smallest closed set.
Okay, but maybe it's simpler than that. You see, if you show that each one of these contains S, I'm just taking forward your reasoning, right? Each one of these sets contains S. Is that obvious? Let us see. Let's go one by one. Okay. So let's take the set B. Does B contain S?
Yes, B by definition.
By definition. Okay. Does C contain S?
Yes, sir. We can use the constant sequences for each of the terms in S.
Exactly. And how about D? Does D contain S? That means that I should take the point small x to be in S itself, right?
Yes, sir. D contains S.
Right, because every neighborhood of such a point in particular includes that point itself, right? So let's just observe that A, B, C, D all contain S. I'm just going to say obvious. Okay. All right. So what else do you want to do? What else do you want to do?
Well, we need to show that B, C, and D are in fact closed now.
Okay, so now you see, here's the thing. So there is some kind of approach, and I am going to take slight issue with the wording. You see, if we show that B, C, and D are closed, it's a good thing, right? By the way, that in itself will not be enough because they may be too large, right? It may not be the largest, it may not be the smallest closed set. But there is the other thing. You see how quickly one can make such things that, okay, in order to prove this statement, we need to show that B, C, and D are closed. Do we need to? Is that the only way of proving it? Is it forced on us this way? Maybe the closed business is a red herring, at least in some of the situations, or at least it is needlessly complicated. Perhaps it is simpler just to take the sets element wise and show that each set is a subset of the other, right? I'm not saying that your approach is wrong. Okay, all I'm saying is that it's not necessarily the only approach. By the way, so I have a prepared proof which I can just go through. But at this stage, really one should try to do these proofs on one's own. Okay, so what shall we do? What shall we do? I'm ready to do at least part of the proof, but I would rather leave all of this for you. Is that fair or is that unfair?
Well, sir, yeah, actually, I think I would like to think about it myself to see how to do it.
So
more efficiently.
let me just make some comments over here, right? So one is that nothing in here is difficult. It is only exercise in language. All right. So each and every one of you should be able to do this. And second, what we can do is that, okay, so let me note the time and I will open it up for the next 2 or 3 minutes. And then whatever ideas people have, you can just tell me. But please don't tell me random ideas. That is, if you can make some observation which takes us to some of the, some way at least, making some connections, I'm happy to sort of hear it. Okay, let me ask you a question. If I asked you, just linguistically speaking, what would be the easiest connections to make, right? A, B, C, and D. In what order should I start making connections? Okay. Which one is the closest to A? This is a psychological question, really, rather than a mathematical question, at least the way I'm formulating it.
I think so. It's D.
Correct. So you see, I agree with that answer. And the reason for this answer is that A and D really have to do only with the topology in terms of the language. So A is about closed sets and D is about open sets. I know that, I can replace the word neighborhood by open set there. So A and D are closed. A and B are fairly close to each other linguistically. Okay, so maybe I can go from A to D. Then what about D? Does D help me? Does D connect with something else?
So I think D and C are connected by the previous claim.
Exactly. So you see the connection between neighborhoods intersecting and being a limit point, or being in terms of, being a limit of a sequence. I have connected it by means of that claim. Okay? So maybe I can go from D to C, and then D and C and D and B, they're both fairly close to E. They're both fairly close, right? So idea. Connect A to D to B and C. Okay. And now you really should be able to do this on your own. Again, I can do this. I can just write down the proof that I have, but it will be far more educational if you do this on your own. And maybe in the beginning of the next class, I will ask you and we can write down the proof, or maybe I will put some of this in the homework. Okay. Any questions? All right, so I'm just going to say exercise. And it's an important exercise for the sake of getting used to the language that we have built, the language of open and closed sets and topology in terms of the metric. Okay, so after all that, let us now come to the definition of continuity. So what did we say? F, a function f from x to y, function between metric spaces is continuous. Okay, let us say continuous at x in x if, and let's trot out our familiar thing, if for all epsilon greater than 0, there exists delta greater than 0 such that, what do we have? Or let's call this point A for fixed point, such that the distance between x and A less than delta implies distance between f of x and f of A is less than epsilon. Okay, good. All right. So what does this say? This really says that x is in the ball at A of radius
Hello,
delta.
sir.
Yes.
Sir, both x and y are having the same distance function, right?
No. Okay. So now here is the thing. So you're absolutely right. Because I say d of x comma a, what is that d? That is the d in the metric space x. And in the target, it is the d from the metric space y. Very often, we will simply not write this, but allow the context to tell you. It may be that x and y are the same metric spaces, okay? But it need not be, okay? So, but for now, okay, in deference to your comment, let us write d sub x and d sub y. It's a very valid point, but we will often let the context determine these things. At least as long as there is no, there is no possibility of confusion. There is only one possible meaning here, right? So, all right. So this one is really synonymous to saying that x is in this ball. And what should that imply? F of x should be in a ball around f of a of, oops, have I just changed my notation? I think around a, and here I have ball of radius epsilon around f of a. Now, this is where life gets interesting, because what we can say is that, i.e., so what are we saying in terms of the picture here? We are saying that if I'm given a ball, so what is given to me? I'm given an epsilon ball around f of a. And what my task is to find a ball around a. I don't care what delta is, as long as it's a positive number, such that by means of f, all of this is mapped to this ball. In other words, what I'm saying is that given any ball around the target point, I can find a ball that is all of which sent inside my target ball. But this is exactly the same thing as saying F inverse of any ball around f of a. What about this? So if I take the inverse images of all of the entire ball, what must happen?
It should contain a ball around X, ball around A.
Correct. So contains a ball. So this is what we mean by continuity of F at a point X. Right? So this is what we have formulated it using open sets. So now when will it happen? So F from X to Y is continuous at all points, just for emphasis. If and only if what happens? F inverse of any ball around F of A. Okay. Okay, so I'm going to write down something over here. Is that correct? There's a slight problem over here.
Sir,
Yes, sir.
it should be F inverse of any ball in Y.
Right. Consider the map from real numbers to real numbers, which is a constant map. F of X equals 0. Okay. Is it true that the inverse image of any ball contains a ball? Any ball.
Yes, because phi is a empty set is a open set, right?
But you see, we are talking about balls. So the formulation becomes awkward because you see, if I take F inverse of some set,
So
that
it should be in
contains
the range.
Right, correct. Any ball intersecting the range. Because you see F inverse of any ball around F of A. So in the formulation above, I need to have a point that contains a point in the range. On the right hand side contains a ball. Do I need to make any change over there? No, you see, because any ball intersecting the range, that means it contains a point F of something. And the moment I take F inverse of F of something, that something is caught in there, no? And so I will get a ball around that point by continuity. Okay. So this formulation starts becoming awkward. But now here comes a slight exclamation mark here. Just set theory.
What is continuity then at the limit points, which is not in the decision?
Okay, so let's come to that later. But right now, I just want to say this in terms of open sets. So
Okay, sir.
So notice that F is continuous if and only if. This is really as an observation now. If and only if F inverse of any open set in Y is open in X. So this may be even double exclamation mark. It's not really difficult based on what we have seen so far, but conceptually it is very interesting because you see all this sort of gory details, epsilons and deltas for all there exists. It has not gone away, but I have built the language in such a way that it can be expressed in simpler language. And when I have simpler language to describe something, that means thinking about it also becomes simpler. Okay, so can we prove this?
So does this condition any open set in Y imply that it has to contain the range? I mean,
right. So now, okay. So what does any open set in Y? So sorry, what did you say about any open set in Y? Does it have to contain a point in the image? Forget whether F is continuous or not. Is it true that that any open set in Y has to contain something in the image of F? Not necessary, no? F could be a constant function. So like f of x equals 0 from R to R. And now consider the open interval 1, 2. Doesn't contain anything in the image. However, what is the inverse image of such a set?
Yeah, here the empty set is open. Here they're asking for open.
Right. So because the empty set is open, right? So here we are good. Okay. So the point is, so by the way, so proof of this. Have you already proved this? You have not quite proved it, you see. So enough to show that F inverse of any ball is open. Why? Because F inverse reserves unions. F inverse of union of, let's say, V alpha is over some index set alpha is union over alpha of F inverse of V alpha. This is just set theory. Think about it for a moment. All right. Now, so why is the inverse image of a ball open? We have already taken care of the case where the inverse image of a ball may be empty, in which case it is open. But suppose the inverse image of a ball is not empty, then why is the inverse image open?
So what's the question?
The question is, why is the if okay, so you're absolutely right. So this is what we need to, okay. I'm sorry, because you're absolutely right to call me out because I'm being sloppy over here. So proof, there are two directions to prove, and I'm showing the forward direction, which is to say, absolutely right to call me out. So I'm assuming that the function is continuous. I want to show that the inverse image of any open set is open, but any open set is a union of balls. So it is enough to show that inverse image of any ball in Y is open in X, if the function is continuous, assuming that the function is continuous. And we already observed that if the inverse image of the ball is empty, then we are done. But in general, why is this the case? And then for the backward direction, suppose F inverse of any open set in Y is open in X. So you see, so this part is still left to do. And we are out of time, so I just want to sort of wrap this up. How about the backward? So that part is left, so left to do. And the reason, so this is left to do, but it is not difficult. And the because is for this enough part. Okay, but how about the backward direction? Suppose I give you that F inverse of any open set is open, open set in Y is open in X. Does that show me that the function is continuous? Is that easy? do this and you can leave. So I really do want everyone to think about this. So suppose it is given to me that F inverse of any open set in Y is open in.
Isn't that equivalent to that if inverse any ball intersecting the range is a subset of is contained in?
Okay.
It's a superset of.
Well, so whether it is equivalent or not is actually a little harder. But you see, if it is
one way implication is simple, that this implies that above.
Right.
That if inverse
So you see, this in particular says that F inverse of any ball is open, right? Okay. So let us just see. This says that so let us say for continuity. So let's prove continuity at A in X. We know, or rather we are given F inverse of B epsilon A is open. And of course, this thing contains A, correct? See, a ball around, B epsilon of F of A, I'm sorry. B epsilon of F of A is open. And the ball around F of A, of course, contains F of A. So its inverse image will contain A. So I have an open set containing A. But an open set containing A has a ball around A. So the radius of that ball is the delta that you want. So let me write this. Is open. And obviously, contains A. Therefore, F inverse of contains a ball around A. Okay, so the backward half is actually quite easy. This is exactly the reasoning that we did up here. I've just rewritten the reason. The forward direction is slight amount of work is left to do. So, we will end for today over here, and let us see what is left. We have to finish the forward direction and the various characterizations of closure that I have written over here. I'm asking you to do. And the exercise that I have given over here earlier about, so you see part A of the exercise is subsumed in the various characterizations of the closure. And part B of the exercise, also we will discuss next time. So what is wrong is that there is an error here in this part, as somebody already noticed here. So this is wrong, but it can be correct this. So find out how to correct this, and we will take up the thread from here on Wednesday.
Recording stopped.
All right, so I tried a new style today, which is to start giving you more exercises for you to work on. These are simple things. Simple does not mean obvious, but simple means that it will give you practice using the words. The only difficulty that is there in what I have left for you to do, which I will do next time right at the beginning. But the only difficulty in here is getting used to the words. So I strongly urge you that you should do this on your own. Watching me do this, sort of rattling through the definitions and connecting them, seeing me do this in class is not going to be that useful.
Sir, can you scroll to the end, sir?
Right, I will certainly scroll to the end. So this is the claim.
Thank you.
Just 1 second. So this earlier thing is just discussion. So claim. By the way, so if some of you want to see this discussion, then I'm happy to go through all of these things now, and I will go through it slowly. We can even have false starts, blind alleys, all of those things. All of those things happen when you are doing mathematics, and you should not resent them, because the purpose that it is serving is that it is forcing you to keep those concepts in your mind, and you are getting familiar with those. So it is time well spent. By the way, so here, right. So here, Ayan Nath, he has given an example which you can check, showing that the original condition is false, and he's also suggested a correction. Right, and Adarsh, I will remember to send the mails to you, relevant mails. Okay, so shall we? So what shall we do? I'm game to discuss any of the things that I asked you to do. All right, so let me ask you some questions. How do you show? So consider the forward direction, the left to do part. So we have to show that, again, let's try to follow our nose. Okay. There are some things just based on the shape of the argument to be proved. There are some things that you get to write for free. What is the nature of the statement? I have to show that some set is open. Correct. How do I show that a set is open?
It's a union of open balls.
Correct. So that means that and even more than that, not only that it is a union of open balls, but that around every point in that set, I have to be able to put a ball with that point as the center. Right? Both of those things are equivalent.
Yes, sir.
Okay. So which one? So how shall we do this? I'm given a ball in the target, and I want to show that its inverse image is open. Any ideas? So let's draw a line over here and maybe draw some pictures. So here is a point here is a ball in the target. So ball in Y. I want to show that its inverse image is open. What should be the first statement of, what should be the first line of the proof? So let us say there is this ball around some point. Do you want to give some notation to this ball, or how shall we set the scene? What are the players? What should we give names to? What should be the initial sentences?
Let X belong to F inverse of ball.
Correct. Now notice that what he's saying is a very good first sentence, because what it is what the way this is going. Okay, so let us say, so what he did not do, and we do not know yet whether this is a good choice or not. But what he did not do was that he did not give a name to the center of this ball or the radius of this ball or anything like that. Correct? Maybe we need to, I don't know. But what is the idea? If you want to show that some set is open, so this is B equal to ball, right? And maybe this set, I don't know, some kind of set will be here. And let us say this is F inverse of B. The idea behind that first sentence is that if I take some point in the inverse image, let us say, I don't know, something. Let us say, okay, let's say A, doesn't matter. I will be done if I show that there is an entire ball around A that is in the inverse image of the ball that I have chosen in Y. Do you notice, for one thing, this thing about the empty, the empty inverse image is already taken care of. Because the moment you say let X be is in, so here is the thing. The first sentence is let A be in F inverse of B. So how is the empty part taken care of? Well, if there is no such A, that means that the inverse image of this ball is empty and the empty set is open. So I don't have to do anything. Right? So it's vacuously true. Now, so let us suppose A is in F inverse of B. Then what do I need to do? I just need to put a ball around that point that is contained in the inverse image of B. Is this easy?
Yes, so like we just take a like ball of around F of A, which is inside ball of P, Y. Yes.
And notice one thing over here. So, is F of A necessarily the center of the ball that I have taken on that I started with? This was center C. F of A need not be C. F of A could be anywhere. F of A could be over here. Right? And in fact, what this tells me is that for the proof to be conceptually better, I should not have gone to balls in Y. It would have been better just to take an open set in Y, because the ball is playing no role over here. Right?
Yes, sir. If we take an open ball, I mean, containing any element C, and we have an F of A in it, then as it is open, we can surround F of A by a ball.
Exactly. And that is the point. That is the point of this proof. But you see, everything that you said, I could have said it for an arbitrary open set. I need not have taken a ball.
Yes, sir.
Right. Yes. So you see what I wrote over here, it is true enough, whatever I said. It is certainly enough to show that F inverse of any ball is open. But it's a needless reduction that I'm doing. And I'm making my life conceptually only more complicated. Because then I'm telling myself that, oh, somehow I should use the ball. There is no need to use a ball over there. So you see, conceptually, it is simpler to think of an open set over here, right? So I can simply say, let me it's not wrong. It is just that, so might as well take where any open set in Y, right? I mean, maybe, okay. So perhaps what I should have done was, I need not have crossed out the picture. I could have crossed out just the ball part of it, right? Okay, so let me do that. Oops, sorry. Okay. So anyway, so you can now complete the proof, which is that may as well take B any open set in Y. Okay, so what was the point? Let me just repeat what he said. A is in F inverse of B. Because f of A is in the open set that was given to me, the set B, that means that I can put an open ball around f of A, which is, so as B is open, we have f of A epsilon ball around contained in P. And now what? By continuity of F, which is given to me, what do I do?
Sir, f of A is an element of the epsilon ball, right?
Yes.
Yeah, okay.
But you see, that is correct, because as B is open, I can put an epsilon ball around any element in that. And because A is in F inverse of B, that precisely means it's synonymous with saying that f of A is in B. And because A is a point of an open set, that means I can put a ball around it inside that open set. Now F is given to be continuous. So what does that tell me? Which is given to me, there exists a delta ball around A such that f of that delta ball is in the epsilon ball around f of A. But that's exactly what we wanted to show, right? Oh, sorry, that there exists a delta ball. Okay, so just 1 second. So such that f of that, but that's exactly saying, i.e., such that f inverse of the epsilon ball contains around f of A, contains the delta ball around A. But that's exactly what it means to show that f inverse of B is open. Because you see, f inverse of that epsilon ball, epsilon ball around f of A, it's just, this is something that is contained in f inverse of B, no? So what did we show? We took an arbitrary point in f inverse of B, and we put a delta ball around that point, totally contained in f inverse of B, by using continuity. So just an observation about this proof. When you see the proof, you will see that there is absolutely nothing to it. But if you are still unsure about the language or learning the language, then it may seem like, what's going on? What did we actually do? So it's the nature of proofs in the beginning, when you are getting used to the language, that, hearing somebody else say the proof, it may not be helpful. You have to somehow sort of do it yourself until you get used to the language. Okay, so shall we stop, or shall we take a look at something else? For example, we could have some discussion of these equivalences.
Sir, I had a question regarding this. So
yes.
showing that B, C, and D are closed won't prove it, right? We also have to prove that B, C, D are subsets of A.
Okay, so I'm sort of leery of saying yes to any kind of have to statement. But let's examine this. Suppose I show that B, C, and D are closed, and suppose I show that they're subsets of A. That will certainly do the job. Because you see, we already observed that they all contain S. Now you are saying that somehow we are going to prove that they are closed. That means they have to contain A, but you're also going to show that they are contained in A. That means they have to equal A. So that is certainly a valid strategy, if you can make it work.
Okay.
Okay, so any other observations? Shall we try, or shall I leave this for you? I'm happy with anything.
Sir, I did not understand the idea that you connect A to D and to B and C. What we have to prove that A is a subset of D or something.
Right. So that is the most obvious thing, right? Of course, see what I can do is the following. I show that A is in either direction. Let us say A is a subset of D, which is a subset of B, which is a subset of C, which is a subset of A. For example, right? I could do that, right? So I don't know what the most efficient way would be, but one can also be just more pedestrian and show that A and D are equal, D and B are equal, and B and C are equal.
Sir,
or A and D are equal, and D is equal to B as well as equal to C, whichever.
To prove that that two sets are equal, we'll have to prove that one is subset of the one.
Yes, exactly, so, exactly. That is true.
Okay, so this one will only have 5 steps.
Right.
The first one that you mentioned.
Right. Or rather 4 steps, right? Just cyclically show A is contained in B, is contained in C, is contained in D, is contained in A, or the other way around, or some other chain, right? But I say that instead of looking for, this is my suggestion, instead of looking for the most efficient way, as a way of forming connections in your mind, try to find a path that allows you to go from anywhere to anywhere. Okay.
Okay.
Right. So it will be. So okay. Since we said connecting A and D, let's just check. Let's just look at D. Right. Every neighborhood of X intersects S. I take all such points. So let's try to follow your idea. Can we show that? So I would like to show that this set is closed. How do I show that a set is closed?
Its complement is open.
Correct. So let's take a point in its complement. And you see, showing that a set is open is a local thing, right? So let's take a point in its complement. What does it mean for a point to be in the complement of D?
There's a neighborhood around X which does not intersect with us.
Correct. So you see, this set D, everything outside it has the property that it has a neighborhood that does not intersect S. Is this set closed? Now, if you could simply replace it by saying that every neighborhood of this point does not intersect D, then we could be done. But okay, that some neighborhood does not intersect D. All right, so sorry, so I'm also blanking out now. Does anybody have any idea?
So like A is like the largest set, which I mean, like it's the complement, like the complement of A is like the largest open set, which does not have any intersect, any.
Exactly.
Yes, sir.
So right, so very good. So that first sentence, its complement is has a good intersection, has a good description. Namely, it is open and it's the largest open set that so say that again.
Yes, sir. Like it doesn't have any intersection with A, like the largest open set.
Right. So right. No, 1 second. It's the largest open set that does not have any intersection with S. That's the description, no?
Yes, sir. Yes, sir.
Right. But of course, it does not have any intersection with A either because it's the complement of A. But in terms of S, it's the largest open set that okay. So maybe see, this is the thing. Let's go with the intersection. So how do I show that D is equal to that intersection? Sorry, I'm just a bit confused over here. And I don't want to look at my notes. So, because these things one should be able to just do on one speed.
Sir, what exactly have we shown till now?
We have shown precious little. All that we have shown is that A, B, C, and D all contain S, and A is closed, and it's the smallest subset.
Okay.
That's all. Okay. So, but okay, let's go a bit further. So we see we do have a description of A. It's the intersection of all closed sets containing S. So what is the complement of this set? It's the union of all open sets not intersecting with S. Right?
Yes, sir.
Right. So what does this have to do with D? I really think that our difficulties at this moment are linguistic difficulties. We really should be able to do A and D, equivalence of A and D fairly easily.
Yeah, so if you take any X in D complement,
okay,
then you can find a neighborhood which does not intersect with S.
Which does not intersect with S. And so such a point has to be,
So that point has to be in A complement.
Correct. Okay, very good. So let's hold that thought. What he just showed is that any point in D complement has to be in A complement. Right? Right? That's what you showed, no?
Yes, sir.
Right. So D complement is a subset of A complement. What that shows is that A is a subset of D. No? Isn't that the case?
Yes, sir.
Yes, so A is a subset of D.
Then you can go the other way, like
How? Okay.
take an x in A complement.
Take an X in A complement.
So it is in some open set which does not intersect with this.
Sorry, no. Just so why? Why? Sorry.
Like A complement is the union of open sets, no, which do not intersect with this.
Right. So okay, exactly. That's just by the explicit construction of A as the intersection of all closed sets containing S. Yes.
Yeah.
So I take something in A. That means it is
in A
correct.
complement.
I mean, correct. So I think so. Okay. So I think the key to this was that really don't show that A and D are equal, but rather show that A complement and D complement are equal. That's what seems to be the key. Correct or no?
Yes, sir.
Right. Okay. So let me see if I can do this to make sure I understand what you just said. Let us suppose X is not in D. That means that there is some neighborhood of X that is disjoint from S. Yeah. And that means that this neighborhood of X is an open set that is disjoint from S. That means this neighborhood of X. So let's just call this U. Okay. So again, to begin with, and I think this is going to be an if and only if thing. X is in D complement if and only if there is some neighborhood of, let's write this down, and then X is in D complement if and only if X is in open U such that U intersection C is phi. Correct? Sorry, U intersection S. What am I saying? Just help me here, please. Is that correct?
Yes, sir.
Okay. But let's now go to, so what does it mean that X is in A complement? I want to show that this is if and only if.
So X is in some open set not intersecting with this.
Correct. So that means X is not in some closed set that contains S. So how can it be in the smallest closed set containing S? I exhibited one particular closed set containing S that it does not belong to. So it cannot be in the intersection. It has already fallen out of this intersection in the first line of the proof.
Wait, sorry, can you repeat?
Correct. So, okay. So what does it mean for X to be in the complement of A? I'm just writing this down. A complement is the union of all open sets not intersecting S. Correct? X minus an intersection, I mean, complement of an intersection is a union of complements, no?
Yeah.
And a closed set containing S, its complement is going to be an open set not intersecting S. So now just see, when I start with X not in D complement, that gives me an open set U like that. but that U satisfies this condition over here. It's one such open set not intersecting S. And you can trace it backwards. If X is in A complement, then that means X is in one open set not intersecting S. Some open set not intersecting S. So I think this is okay. Check. In fact, the backward direction is very easy. I don't even have to have, see, if X is in A complement, then A complement itself is an open set not intersecting S, in which X belongs. So the fact that A complement is contained in D complement is easy. It's the one that you told me that was harder, which was that D complement is contained in A complement. Sorry.
Yeah, I understand.
Right? Again, what is happening is only language. So let me even just see this. And even easier. Not backward. Let's state this in terms of that. So A complement contained in D complement easier, because A complement is union of all, or even we don't have to say that, because A complement is itself open. No. Remember, A is a closed set. So A, D, and D are really just a dictionary, just like going open and closed. Now, every neighborhood of X intersects S is the same thing as B and C. Shall we do this? This should also not be difficult. In view of the claim that we have proved. Remember the claim? Limit point means that every neighborhood contains a point of S other than X. So in fact, showing that B and C are equal is fairly easy. All right, shall we do this, or shall I leave this for you? Okay, so let's look at B and C. Is either one of the inclusions easy? B is a subset of C and C is a subset of B. Is at least one of them easy? One of them is obvious. Which one?
B subset of C.
Yeah, absolutely. Because I can take to show that S is contained in C, I can just take the constant sequence. And for all the limit points, I'm already given such a sequence on platter. In fact, with a stronger condition that none of the essence is X itself. So B is subset of C is very easy. Why is C a subset of B? And one way to say this is, okay, suppose I want to show that C is a subset of B. Let us look at the shape of the statement. It says that C is a subset of a union. So one way to prove is that Suppose I have a point in C. I want to show that it belongs to a union of two sets. So I get to say, suppose I have a point of C which does not belong to one of the sets, then it belongs to the other. You follow what I'm saying? So I get to, for free, I get to write down the following sentence. Let us suppose X is a limit of some sequence in S such that the limit of this sequence does not belong to S. Then it is a then this point X is a limit point of S. Okay, is this all right?
So, or we can prove that if for some X in C, if X does not belong to S or is not one of the limit points, then we get a contradiction.
You can do that also. Yes. I just, just sort of one remark, and it's really a matter of taste rather than, but often there is a temptation sometimes to just for free, just to begin the proof by saying suppose not and derive a contradiction. It's a perfectly valid technique if you can make it work. But in some situations, you see that the proof by contradiction is not really necessary. You can actually give a direct proof. Sometimes it is, of course, required. You cannot prove that square root of 2 is irrational without contradiction. But sometimes you can really give a direct proof. And direct proofs sometimes, at least sometimes when possible, they have the advantage of making it clearer what is going on. In this particular case, you can certainly do what you said, but the more direct proof will have the advantage of actually constructing a sequence. So, I mean, I will hear you out if you have a suggestion. But you see, the strategy that I suggested, I'm by no means arguing that it is the only strategy. But what it will do is that if I am given something in C, that is, if I am given X to be the limit of some sequence, and if X is not in S, then it is actually possible to produce another sequence which will exhibit X as a limit point.
Right.
And this sort of, right, and this sort of suggests itself, right? Because how could this see? My first idea would be I want to show something is a limit point. That means I have to produce a sequence. Well, I'm already given a sequence. So why might this sequence not work? Why might it not work? I mean, I'm also, I'm also not completely done over here. So why might this sequence not work? So let us see the definition. Let's see the difference between the kind of sequence given over here and the kind of sequence that is required for the limit point. That means none of the essence means all the points have to be different from X. So what if not all points are different from X?
So we can just delete the X elements from the sequence.
You can just delete the X elements. So the point is, so if I delete all the X elements, I should still have, okay, so one thing we already know, it's going to be the exact same proof, that if I have a sequence that converges, then the limit of any subsequence is also going to be the same limit, right? Yeah, I mean, this was
I think excuse me, sir. I think I have another idea for B and C. We already found out that S is a part of both B and C.
Right. Sorry. So just 1 second, please. I mean, I think you're suggesting some idea. So I want to come to the idea, but let's finish this off. Okay. So is there any problem why this just delete all the excess? Is there any potential problem with this?
So it could be that like it would the sequence would be finite, but that can't be the case because then like X will have to be like at the tail of the sequence, like
Correct.
always.
So you see here is the point. So so first comment was that if I delete the excess, then if whatever is remaining the sequence, whatever sequence remains, if it is a sequence, then the limit of that subsequence would still have to be X, correct? The limit of a subsequence is the same as the limit of the sequence. So the point is that after deleting X, I do not have a sequence. That means I have only finitely many terms left. But what does that mean? That means that the original sequence must have been eventually X all the way. That's the only way in which this can happen, right? That's the only way in which this idea can fail. But if the original sequence was eventually X all the way, then what would that mean?
So could you repeat what you just said?
Okay, so I think maybe okay. So I think it's a bunch of small steps. What I'm trying to show is that C is a subset of B. Okay. And I'm sorry, so there is a pending idea. We will come to that idea in just a couple of moments. I'm trying to show that C is a subset of B. The way I'm going to set this up is by saying that suppose something is in C. That is an element X, that is a limit of some sequence in the set S. I want to show that such a thing is in B. So I'm saying the way I will show is that by saying, suppose this X is not in S, then it must be a limit point of S. Okay. So is the setup clear? Or should I write this down somewhere? See, unfortunately, I don't have space. Okay, I will just use this space and I will erase all this later on. Okay. So the claim is that C is in B. That is the claim. Let X is in C, but not in S. So claim X is a limit point of S. So we are given Sn going to X, right? Just delete all Sns that are equal to X. If the remaining entries are going to, so now the remaining entries are all by construction different from X. And limit of this subsequence would also be the same as the limit of the original sequence, but the limit of the original sequence was X. So I exhibited it as a limit point. Limit of a sequence of points, none of which is X. And the limit is X. Is this okay so far? Or still I'm not making it clear? Anyway, so but I have to say some more words for this strategy to work. Is that when I just drop all the occurrences of the undesired element from the sequence, what I'm left with might not be a sequence. A sequence needs to be an infinite sequence, right? Only then I can take a limit. So the only way this could fail is that beyond a certain point, every element of the sequence is X. But if every element of the sequence were X, then what would happen? The limit would also be X. But what did I just say? I claimed that this X is a limit, but I claimed that X is in C, but it is not in S. That was my hypothesis. Sorry, I'm confused myself now. I thought this proves it, but is there a problem?
Yes, like if its limit like a limit is X, then like since X is element of S, like the limit will also be an element of S. Like
right. The only thing is, why is X an element of S?
Because like we took the limit of Sn to be X. Like so if like the tail of the sequence is just X.
Oh, sorry. Yeah. But I mean, if X were in no, just 1 second. Every neighborhood contains a point other than, sorry, just 1 second. No, I have confused myself. S minus X. Sorry, no, I mean, sorry. I'm sorry to have exposed you to this verbal diarrhea. See, the point is I have already assumed that X is not in S, no? So I don't have to really say anything more. Just see, because if X were in S, then I'm done. And if X is not in S, then the limit is the, in the set C, I'm given some sequence Sn in S, no? But Sns are in S and X is not in S. So it's automatically a legit sequence. Just look over here, the definition. Each Sn has to be an element of S, but other than X. I'm sorry, I think that I just tied myself in knots because I was not thinking straight. I think it's much easier than that. Just please check the proof. Given Sn in X, the same. What is there? Why would this sequence be wrong? The only reason why this sequence would be wrong would be if some of the Sns were X. But X is not in S. And all the Sns are in S. How can two of them be the same? Sorry, this was much easier than what I thought. So the fact that B and C are equal is, I think, more or less, I mean, I hate to use the word trivial, but it really is not a big deal. Sorry, I made it. I was not thinking straight. So I think this is correct, and it is much easier than I thought. Okay, so now somebody had some idea about thinking about B and C. So please go ahead. Sorry, I think who was it? I don't recall, but somebody did have some way of thinking about B and C, no?
So I guess it was Pratham, and actually I guess he left because like we have a next class in like 2 o'clock.
Oh, sorry. I'm very sorry. So you should just go ahead.
Yes, sir.
Yeah. By the way, I mean, just in general, feel free to leave absolutely anytime. You do not have to stay. So we'll continue on Wednesday. Thanks, and sorry. So bye.
Yes, thank you, sir.